Number 1, let s equal to 2t minus ln of t and y equal to 2t plus ln of t. Find the equation of the tension line at t equal to 1. In order to find the equation of tension line, we must find the point at t equal to 1 and the slope at t equal to 1. Let's find the point first. When t equal to 1, x equal to 2 times 1 minus ln of 1. ln of 1 is 0, so x is 2. Y equal to 2 times 1 plus ln of 1, which is also 2. So at t equal to 1, the point on the curve is 2, 2. Next, we have to compute the slope at t equal to 1. In order to find the slope, let's find the derivative first. dy over dx is dy over dt over dx over dt. Here we take the derivative for x and y with respect to t. dy over dt is 2 plus 1 over t. dx over dt is 2 minus 1 over t. For x and y, take the derivative with respect to t. Then, to make it a little simpler, I can multiply top and the bottom by t. To make the expression a little easier, I can multiply the top and the bottom by t. So the derivative can be rewritten as 2t plus 1 over 2t minus 1. That's the derivative of the curve. Next, I try to find the slope of tension line at t equal to 1. So for the slope of tension line, I plug in 1 into the derivative. I have 2 times 1 plus 1 over 2 times 1 minus 1, which is 3 over 1 equal to 3. So the slope of tension line at t equal to 1 is 3. Once I know a point and know the slope, I can find the equation of the line. Y minus 2 equal to 3 times x minus 2. If I simplify, I make y minus 2 equal to 3x minus 6. So y equal to 3x minus 4. That's the equation of the tension line at t equal to 1. Part B. Find all points where the tension line is either horizontal or vertical. When the tension line is horizontal, its slope must be 0, which means the derivative must be 0. When the tension line is vertical, its slope must be undefined, which means the derivative must be undefined. So in part B, for horizontal tension line, since we try to make the slope 0, I set the numerator equal to 0. For vertical tension line, since I try to make the slope undefined, so I make the denominator of the derivative equal to 0. I set 2t minus 1 equal to 0. Then solve an equation for t. If I solve the first equation, I get t equal to negative half. If I solve the second equation, I get t equal to a half. That means when t equal to negative half, the tension line is horizontal. And when t equal to a half, tension line is vertical. Next, I plug in each t to find the points. If I plug in t equal to negative half into the function x and y, I get 2 times negative half minus ln of negative half, which is undefined. ln of negative half is undefined. So this point does not exist. That means there's no point that has horizontal tension line. This answer is rejected. That means there's no point that has horizontal tension line. Next, I plug in half into the function x and y. I get x equal to 2 times a half minus ln of a half, which is 1 minus ln of half. ln of half can be rewritten as negative ln of 2. So x can be rewritten as 1 plus ln of 2. And for y, do the same thing. Plug in half into function y. 2 times half plus ln of half. 2 times half plus ln of half, which is 1 minus 1 plus negative ln of 2. That can be rewritten as 1 minus ln of 2. So the point here is sy equal to 1 plus ln of 2, comma 1 minus ln of 2. So there's no point that has horizontal tension. That has horizontal tension line. At point 1 plus ln of 2, comma 1 minus ln of 2, the tension line is vertical. Part C. Determine for which value of t is the curve concave up or concave down. So for concavity, we try to use the second derivative test. Second derivative d squared y dx squared is d dt of dy over dx over dx over dt. So use the formula. We first of all take derivative for dx, dy over dx. Here we can use quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom over the bottom square over ds over dt. For ds over dt, we take derivative for x. Take derivative for x. We have 2 minus ln of t. Then simplify the expression. The numerator, I can distribute 2 first. I get 4t minus 2 and distribute 2 here. I get minus 4t minus 2 over 2t minus 1 square. The denominator 2 minus 1 over t can be rewritten as 2t minus 1 over t. Then simplify the numerator. 40 and 40 can cancel. Negative 2 minus negative 2 is negative 4 over 2t minus 1 square. When we have a fraction divided by a fraction, I flip the second fraction over. So I have t over 2t minus 1. Then multiply the numerator and denominator. Multiply numerator to numerator, denominator to denominator. I have negative 4t over 2t minus 1 cube. This is the second derivative. Next, we try to find a critical point. And make second derivative test. So I set both the denominator and numerator equal to 0. Set negative 4t equal to 0. And set 2t minus 1 cube equal to 0. Solve the equation for t. I get t equal to 0 and t equal to a half. T equal to 0. This 0 is not on the domain. This 0 is not on the domain. Ln of 0 is undefined. This 0 is not on the domain, so it's rejected. The only critical point is a half. The only critical point is half. Next, let's make number line test. The domain of the function starts from 0. Half is a critical number. Let's make second derivative test. Let's pick testing value for t. Let's pick some test value for t. Between 0 and a half, I can pick a quarter to be a test number. Then for a number greater than a half, I can pick 1 to be a test number. Then plugging t into the second derivative. Then plugging t into the second derivative. If I plug in a quarter, negative 4 times quarter is negative 1. 2 times quarter is half. Half minus 1 is negative half. Negative half cube is negative. Double negative is positive. If I plug in 1 on the numerator, negative 4 times 1 is negative 4, which is negative. If I plug in 1 on the denominator, 2 times 1 is 2, and 2 minus 1 is 1. 1 cube is positive. Negative number over positive number is negative. So for t greater than 1, for t greater than half, the second derivative is negative. When the second derivative is positive, the curve is concave up. When the second derivative is negative, the curve is concave down. So when t is between 0 and a half, the curve is concave up. when t is greater than half. When t is greater than half, the curve is concave down. Number 2, let s equal to t squared minus 1 and y equal to t cubed plus 1. Part A, find the area between the curve and the x-axis for t between 0 and 4. So area between the curve and the x-axis, the formula is y dx. So here we have t is from 2 to 4, y is t cubed plus 1, x is t squared minus 1. That means dx is 2t dt. So y dx, y times dx, dx is 2t dt. Then take the antiderivative. We can first of all distribute 2t. I get 2t to the power of 4 plus 2t dt. Then take antiderivative. I get 2 over 5 times t to the power of 5 plus t squared. Evaluate from 2 to 4. If I plug in 4, 4 to the power of 5 is 1024 times 2 is 2048 over 5. If I plug in 4 here, 4 squared is 16. Plug in 2, 2 to the power of 5 is 32. 32 times 2 is 64. I get 64 over 5 plus 2 squared is 4. Then use calculator. The final answer is 2044 over 5. That's part A. Part B. Find the area between the curve and the y-axis. Find the area between the curve and the y-axis. For area between the curve and the y-axis, the formula is x dy. And here, since y is t cubed plus 1, since y is t cubed plus 1, dy is 3t squared dt. And here t is from 2 to 4. X times dy. X is t squared minus 1. T squared minus 1 times dy. dy is 3t squared dt. Then distribute 3t squared. I have 3t to the power 4 minus 3t squared dt. Next, take antiderivative. I get 3 over 5 t to the power 5 minus 3 over 3, which is 1 t to the power 3. Evaluate from 2 to 4. If I plug in 4, 4 to the power 5 is 1024. 1024 times 3 is 3072 over 5. If I plug in 4 here, 4 to the power 3 is 64. Then substitute 2 for t. 2 to the power 5 is 32. 32 times 3 is 96. I get 96 over 5. Minus 2 to the power 3 is 8. Then use calculator. The final answer is 2696 over 5. Number 2, part C. Find the length of an arc on quadrant 2. So in order to find the length of arc on quadrant 2, let's sketch the graph first. First of all, let's make a table. Make a table for t, x, and y. Let's pick some positive value and negative value for t. So I can choose t to be -2, -1, 0, 1, 2. Pick some positive and negative value for t. Then for each t, we try to find x and y. If I plug in -2, Negative 2 squared is 4. 4 minus 1 is 3. Negative 2 cubed is negative 7. Sorry, negative 2 cubed is negative 8. Negative 8 plus 1 is negative 7. If I plug in negative 1, I get 0, 0. If I plug in 0, I get negative 1 and 1. If I plug in 1, I get 0 and 2. If I plug in 2, I get 3 and 9. Then plot these points in the xy plane. When x is 3, y is negative 7. When x is 3, y is negative 7. 1, 2, 3, 4, 5, 6, 7. When x is 0, y is 0. So that's the origin. When x is negative 1, y is 1. When x is 0, y is 2. When x is 3, y is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then connect these points. Connect these points. Connect this point using smooth curves. We're looking for the length of an arc on quadrant 2. This arc here in quadrant 2. So we can see that the endpoint of this arc, they both locate in the y-axis. The endpoint of this arc locate in the y-axis. For points in the y-axis, x-coordinate must be 0. For points in the y-axis, the x-coordinate must be 0. So in order to find these 2 points, I set s equal to 0. Solve for t. So set s equal to 0. Solve for t. T squared equal to 1. So t equal to positive and negative 1. When t equal to negative 1, the point is 0, 0. So at this point, t is negative 1. When t equal to positive 1, the point is 0, 2. The point is here. So for an arc length here, take t from negative 1 to 1. The arc length formula is integral from a to b. Square root of dx over dt squared plus dy over dt squared dt. So here in arc length, I take t from negative 1 to 1. Square root of dx over dt squared plus dy over dt squared. S equal to t squared minus 1, so dx over dt is 2t. Y equal to t cubed plus 1. So dy over dt is 3t squared. So plug in. I have 2t squared plus 3t squared squared dt. Then take integral. Let me simplify the square root first. Here I have square root of 4t squared plus 9t to the power 4 dt. I can factor t squared out. I get square root of t squared times square root of 4 plus 9t squared dt. Now, be very careful. Square root of t squared is absolute value of t. Absolute value of t, if t is positive, is greater or equal to 0, absolute value of t is the same as t. If t is less than 0, absolute value of t is negative t. Be very, very careful. So from negative 1 to 1, t may be positive, may be negative. So here I need to separate this integral into two integrals. From -1 to 0. Absolute value of t times 4 plus 9t squared dt. Plus integral from 0 to 1. Absolute value of t times square root of 4 plus 9t squared dt. When t is from -1 to 0, t is less than 0. So absolute value of t is negative t. When t is between 0 and 1, t is greater than 0. So absolute value of t is t. Then take antiderivative. For both integrals, we can apply u substitution. Let u equal to 4 plus 9t squared. Then du equal to 18t dt. So first integral can be rewritten as -1 over 18. Integral from, if I plug in 0, I get 4. If I plug in -1, I get 13. Integral from 13 to 4. Square root of u du. Second integral, if I make a u substitution, I get positive 1 over 18. Integral, if I plug in 1, I get 13. If I plug in 0, I get 4. Square root of u du. And we know square root of u can be rewritten as u raised to a half. Square root of u can be rewritten as u to a half raised to a half. Then take antiderivative. I get -1 over 18 times u raised to 3 over 2 divided by 3 over 2, which means times the reciprocal 2 over 3. Evaluate from 13 to 4. The other integral is u raised to 3 over 2 times 2 over 3. Evaluate from 4 to 13. 1 over 18 times 2 over 3. If I cancel here, I get 1 over 1 on the top, 9 on the bottom. So that's -1 over 27. Plug in 4. 4 raised to 3 over 2 is a. If I plug in 13, 13 raised to 3 over 2 is 13 radical 13. For the second integral, 1 over 18 times 2 over 3 is 1 over 27. Plug in 13. 13 raised to 3 over 2 is 13 radical 13. If I plug in 4, 4 raised to 3 over 2 is a. Factor, pull out 1 over 27. I have -a plus 13 radical 13 plus 13 radical 13 minus a. Then combine like terms. I have 26 radical 13 minus 16. If I factor 2 out, the answer is 2 over 27 times 13 radical 13 minus a. Number 3, let r equal to 1 minus sine theta. Part A, find the equation of tangent line at theta equal to pi. In order to find the equation of tangent line, we must know the point when theta equal to pi. And we must know the slope of the tangent line when theta equal to pi. Let's find the point first. We know x is always r cosine theta. Y is always r sine theta. When theta equal to pi, r equal to 1 minus sine pi. We plug in pi here to find r. And we know that sine pi is 0. 1 minus 0 is 1. So when theta equal to pi, r is 1. Next, we can find x and y. X is r cosine theta. When theta equal to pi, r is 1 times cosine theta. Cosine theta is cosine pi. We know that cosine pi is negative 1. 1 times negative 1 is negative 1. Y is r sine theta. When theta equal to pi, r is 1. Sine theta is sine pi. And we know that sine pi is 0. 1 times 0 is 0. So when theta equal to pi, the point on the curve is negative 1, 0. Next, we try to find the slope of tangent line when theta equal to pi. Let's compute the derivative first. dy over dx can be rewritten as dy over d theta over dx over d theta. Since y is r sine theta, I can use product rule to find dy over d theta. Use product rule. Derivative of the first times the second plus the first times derivative of the second. And on the bottom, for ds over d theta, use product rule again. Derivative of the first times the second plus the first times derivative of the second. Derivative of cosine is negative sine. Then plug in dr over d theta. Since r is 1 minus sine theta, dr over d theta is negative cosine theta. So plug in, I get negative cosine theta times sine theta plus r. R is 1 minus sine theta times cosine theta. On the bottom, dr over d theta can be, dr over d theta is negative cosine theta times cosine theta minus r. R is 1 minus sine theta times sine theta. Then plug in. For slope of tangent line, we plug in theta equal to pi into the derivative. Plug in theta equal to pi. I have negative cosine pi times sine pi plus 1 minus sine pi times cosine pi. On the bottom, I get negative cosine pi times cosine pi minus 1 minus sine pi times sine pi. On the numerator, since sine pi is 0, first term becomes 0. Second term, 1 minus sine pi is 0, I get 1. Cosine pi is negative 1. On the denominator, I get negative cosine pi is negative 1. Another cosine pi is another negative 1. And second term, since sine pi is 0, the second term becomes 0. So together we have negative 1 on the top and negative 1 on the bottom. Negative 1 over negative 1 is positive 1. So the slope of tangent line, when theta equal to pi, the slope is 1. Next, we can find the equation of tangent line. Use the point and the slope. Y minus 0 equal to 1 times x minus negative 1. Use the point and the slope, we can find the equation of tangent line. Y minus 0 is 1. Y minus 0 is y. This should be 1. I get x plus 1. That's the equation of tangent line when theta equal to pi. Number 3, part B. Find all points when the tangent line is either horizontal or vertical. We know that when tangent line is horizontal, its slope must be 0. And when the tangent line is vertical, its slope must be undefined. This is the derivative. Let me first of all simplify the derivative. dy over dx on the numerator, it can be rewritten as negative cosine theta sine theta plus cosine theta minus cosine theta, sine theta. On the denominator, if I distribute sine theta, it can be rewritten as negative cosine squared theta minus sine theta plus sine squared theta. In the numerator, negative cosine theta, sine theta, and negative cosine theta, sine theta, if I combine like term, it's negative 2 sine theta cosine theta plus cosine theta. On the denominator, we have negative cosine theta. Let me put sine squared theta in the front. I have sine squared theta minus cosine squared theta minus sine theta. Then, for horizontal tension line, I set the numerator equal to 0. And for vertical tension line, I set the denominator equal to 0. Solve the equation for theta. So, for horizontal tension line, I set the numerator equal to 0. 2 sine theta cosine theta plus cosine theta equal to 0. Solve this equation for theta. I can first of all vector cosine out. If I pull out cosine theta, I have negative 2 sine theta plus 1 equal to 0. Which means either cosine theta equal to 0 or sine theta equal to a half. Next, we try to solve for theta. If we sketch the graph from the function r equal to 1 minus sine theta, the graph looks like this. That's when theta is 0. When theta is pi over 2, we are here. And when theta is pi, we are here. When theta is 3 pi over 2, we are here. When theta is 2 pi, go back to 0. So from 0 to 2 pi, it completes one cycle. In order to find the point where the tension line is either horizontal or vertical, we are looking for theta from 0 to 2 pi. Cosine theta equals 0 means theta must be pi over 2 and 3 pi over 2 from 0 to 2 pi. Sine theta is a half. The reference angle, from the reference angle, we know that sine of pi over 6 is a half. So reference angle is pi over 6. Angle theta. For angle theta, we know sine function is positive in quadrant 1 and quadrant 2. So in quadrant 1, angle theta is pi over 6. In quadrant 2, angle theta is pi minus pi over 6, which is 5 pi over 6. So there are 4 solutions here. Theta equal to pi over 2, theta equal to 3 pi over 2, theta equal to pi over 6, theta equal to 5 pi over 6. Next, for vertical tension line. For vertical tension line, we set the denominator equal to 0. Set the denominator equal to 0. We have sine squared theta minus cosine squared theta minus sine theta, theta equal to 0. We know that cosine squared theta can be rewritten as 1 minus sine squared theta. If we combine like terms, sine squared theta plus another sine squared theta is 2 sine squared theta minus sine theta minus 1. If I factor this equation, it can be rewritten as 2 sine theta in the first parenthesis, sine theta in the second parenthesis, negative 1, positive 1. Solve an equation for theta. Sine theta equal to negative a half. Sine theta equal to positive 1. And from 0 to 2 pi, we know sine function is negative in quadrant 2 and in quadrant 3 and quadrant 4. Sine function is negative in quadrant 3 and quadrant 4. Here reference angle is pi over 6. For sine function in quadrant 3, angle theta is pi plus the reference angle. It's 7 pi over 6. For angle in quadrant 4, angle theta is 2 pi minus pi over 6, which is 11 pi over 6. And from 0 to 2 pi, if sine theta is 1, theta must be 3, it must be pi over 2. So here we have 3 solutions. Theta equal to 7 pi over 6, 11 pi over 6. Or pi over 2. So we know that when theta is pi over 2, 3 pi over 2, pi over 6, 5 pi over 6, the tension line is horizontal. When theta is 7 pi over 6, 11 pi over 6, and pi over 2, tension line is vertical. But do we see a problem here? When theta is pi over 2, the tension line cannot be both horizontal and vertical at the same time. When theta is pi over 2, the tension line cannot be both vertical or horizontal at the same time. So here, in this situation, we must take a limit for the derivative. In this situation, we must take a limit for the derivative. If the limit, take a limit as theta approach to pi over 2, we take a limit for the derivative as theta approach to pi over 2. If the limit is 0, then the tension line is horizontal. If the limit is infinity, the tension line is vertical. But if the limit is neither 0 nor infinity, then tension line is neither horizontal nor vertical. So let's take a limit for the derivative. This is the derivative. Negative 2 sine theta cosine theta plus cosine of theta over sine square theta minus cosine square theta minus sine theta. The numerator can be rewritten as negative sine 2 theta plus cosine theta. If I use double angle formula for 2 sine theta cosine theta, the denominator can be rewritten as negative cosine 2 theta minus sine theta. If I use double angle formula for sine square theta minus cosine square theta, I get negative cosine 2 theta. Then if I plug in pi over 2, to the numerator, 2 times pi over 2 is pi, sine pi is 0. Cosine pi over 2 is also 0. Negative 0 plus 0 is 0. The denominator, if I plug in pi over 2 times 2 is pi. Cosine pi is negative 1. Negative 1 is positive 1. And sine pi over 2 is 1. 1 minus 1 is also 0. We have 0 over 0. So we can apply L'Hopital's rule. If we apply L'Hopital's rule, take derivative for each denominator and numerator. On the top, I have negative 2 cosine 2 theta minus sine theta. On the bottom, I have positive 2 sine 2 theta minus cosine theta. If I plug in pi over 2 again, 2 times pi over 2 is pi. cosine pi is negative 1. Sine pi over 2 is 1. If I plug in pi over 2 to the denominator, 2 times pi over 2 is pi. Sine pi is 0. Cosine pi over 2 is 0. So denominator is 0. On the numerator, negative 2 times negative 1 is 2. 2 minus 1 is 1. 1 over 0 is either positive or negative infinity. 1 over 0 is either positive or negative infinity. So if the limit is infinity, that means at pi over 2, when theta is pi over 2, the tangent line is vertical. The tangent line is vertical. So when theta equal to pi over 2, the tangent line is vertical. So for horizontal tangent line, this must be rejected. We have three solutions. Theta equal to 3 pi over 2, pi over 6, and 5 pi over 6. When theta is 3 pi over 2, r equal to 1 minus sine 3 pi over 2. Sine of 3 pi over 2 is negative 1. 1 minus negative 1 is 2. So x is r cosine theta 2 times cosine 3 pi over 2, that's negative 2. Sorry, cosine 3 pi over 2 is 0. Cosine 3 pi over 2 is 0. 2 times 0 is 0. Y equal to r sine theta, that's 2 times sine 3 pi over 2. Sine 3 pi over 2 is negative 1. 2 times negative 1 is negative 2. So when theta is pi over 3 pi over 2, the point is 0, comma negative 2 on the curve. When theta is pi over 6, r equal to 1 minus sine pi over 6. Pi over 6, sine pi over 6 is half. 1 minus half is half. So x is r cosine theta, which is half times cosine pi over 6. Cosine pi over 6 is radical 3 over 2. So x coordinate is radical 3 over 4. Y coordinate is r sine theta, which is half times sine pi over 6. Sine pi over 6 is half. Half times half is a quarter. So when pi over 6, the point is radical 3 over 4, comma 1 over 4 on the curve. When theta is 5 pi over 6, r is 1 minus sine 5 pi over 6. Sine 5 pi over 6 is also a half. 1 minus half is a half. So x is r cosine theta, half times cosine 5 pi over 6. Cosine 5 pi over 6 is negative radical 3 over 2, which is negative radical 3 over 4. Y is r sine theta, which is half times sine 5 pi over 6, which is half times half. Half times half is a quarter. So when theta is 5 pi over 6, the point on the curve is negative radical 3 over 4, comma 1 over 4. And for vertical tension line, it occurs when theta equal to 7 pi over 6, 11 pi over 6, and pi over 2. Theta is 7 pi over 6, 11 pi over 6, or pi over 2. When theta is 7 pi over 6, R is 1 minus sine 7 pi over 6. Sine 7 pi over 6 is negative half. 1 minus negative half is 3 over 2. X is R cosine theta, which is 3 over 2 times cosine 7 pi over 6. Cosine 7 pi over 6 is negative radical 3 over 2, which is negative 3 radical 3 over 4. Y is R sine theta, which is 3 over 2 sine 7 pi over 6 times sine 7 pi over 6. Sine 7 pi over 6 is negative half. So, which is, if we multiply, we get negative 3 over 4. So when theta is 7 pi over 6, the point on the curve is negative 3 radical 3 over 4, comma, negative 3 over 4. When theta is 11 pi over 6, R is 1 minus sine 11 pi over 6. Sine 11 pi over 6 is negative half. 1 minus negative half is 3 over 2. So X is R cosine theta, which is 3 over 2 times cosine 11 pi over 6. That's 3 over 2 times cosine 11 pi over 6. Cosine 11 pi over 6 is positive radical 3 over 2. If we multiply, we have 3 radical 3 over 4. Y is R sine theta, which is 3 over 2 times sine 11 pi over 6. Sine 11 pi over 6 is negative half. 3 over 2 times negative half is negative 3 over 4. So we have, when theta is 11 pi over 6, the point on the curve is 3 radical 3 over 4, comma, negative 3 over 4. Next, when theta is pi over 2, when theta is pi over 2, R is 1 minus sine pi over 2. Sine pi over 2 is 1. 1 minus 1 is 0. S is R cosine theta, which is 0 times cosine pi over 2, which is 0. Y is R sine theta, which is 0 times sine pi over 2. Sine pi over 2 is 1. 0 times 1 is 0. So when theta is pi over 2, the point on the curve is 0, 0. Combine everything together. So horizontal tension line occurs at points 0, negative 2, radical 3 over 4, 1 over 4, and negative radical 3 over 4 and a quarter. vertical tension line occurs at points -3, radical 3 over 4, comma, -3 over 4, comma, 3, radical 3 over 4, comma, -3 over 4, and 0, 0. Number 4, part A. Let R equal to 1 plus 2 sine theta. Find the area of a region enclosed by the inner loop and the area enclosed by the outer loop. The area formula is half of R squared d theta, and take integral theta from alpha to beta. The formula itself is simple. The hardest part is find the upper and lower limit. So in order to find the upper and lower limit, let's sketch the graph first. R equal to 1 plus 2 sine theta. If we sketch the graph, it looks like this. It starts from here. If we follow the path of this graph, we can see that the curve goes this way. The inner loop starts at the origin. And when we complete the inner loop, it goes back to the origin. When we start the inner loop, it starts from the origin. And when we complete the inner loop, it goes back to the origin. So we try to find out when the curve touches the origin. So I set R equal to 0, and the origin R is 0. I set R equal to 0. So set R equal to 0. We have 1 plus 2 sine theta equal to 0. Then solve the equation for theta. Sine theta is -1/2. Reference angle, we know sine pi over 6 is 1/2. So reference angle is pi over 6. Reference angle is always positive. So reference angle is pi over 6. And we know sine function in quadrant 3 and quadrant 4 is negative. Sine function in quadrant 3 and quadrant 4 is negative. For angle in quadrant 3, theta is pi plus the reference angle. Here we get 7 pi over 6. For angle in quadrant 4, angle theta is 2 pi minus the reference angle. Here we have 11 pi over 6. So when theta is 7 pi over 6, it starts in the inner loop. When theta is 11 pi over 6, it completes the inner loop. So here we can see that when theta is 7 pi over 6, it starts in the inner loop. And when theta is 11 pi over 6, it completes the inner loop. So that's an area of the inner loop from 7 pi over 6 to 11 pi over 6. Then using the formula, half of R squared, R is 1 plus 2 sine theta, and square times d theta. Next, solve the integral. Expand the perfect square first. I get 1 plus 4 sine theta plus 4 sine square theta d theta. If I distribute half, I get half plus 2 sine theta plus 2 sine square theta d theta. Next, I can use half angle identity. For sine square theta. half angle formula for sine squared theta is half of 1 minus cosine 2 theta d theta. Two times half is 1, so I get 1 minus cosine 2 theta d theta. If I combine like terms, half plus 1 is 3 half, plus 2 sine theta minus cosine 2 theta d theta. Next, take antiderivative. We got 3 over 2 theta plus negative 2 cosine theta minus half of sine 2 theta. Evaluate from 7 pi over 6 to 11 pi over 6. Then plug in 11 pi over 6 and 7 pi over 6, taking the difference. If I plug in 11 pi over 6, I get 3 over 2 times 11 pi over 6 minus 2 cosine 11 pi over 6 is positive radical 3 over 2. If I take 2, plug in 11 pi over 6, take 2 times 11 pi over 6, I get 11 pi over 3. Sine 11 pi over 3 is negative radical 3 over 2. If I plug in 7 pi over 6, I have 3 over 2 times 7 pi over 6 minus 2 times cosine 7 pi over 6 is negative radical 3 over 2 minus half of, if I plug in 7 pi over 6 here, 2 times 7 pi over 6 is 7 pi over 3. Sine 7 pi over 3 is positive radical 3 over 2. So here, if I combine like terms, 11 pi over 6 minus 7 pi over 6 is 4 pi over 6. 4 pi over 6 can be rewritten as 2 pi over 3. 2 pi over 3 times 3 over 2 is pi. Cancel 2 here. I get negative radical 3 minus triple negative is also negative. That's 2 radical 3. Here, double negative is positive. Again, here double negative is also positive. Radical 3 over 4 plus radical 3 over 4 is radical 3 over 2. Combine like terms, I get pi minus 3 radical 3 over 2. Next, we're looking for an area enclosed by an outer loop. For an area enclosed by an outer loop, we can first of all start from 0. Go from 0 to 7 pi over 6. Half of r squared d theta. Plus another piece here. From 11 pi over 6 to 2 pi. Half of r squared d theta. So first of all, we go from 0 to 7 pi over 6. Then we go from 11 pi over 6 to 2 pi. That's the area enclosed by the outer loop. But if we solve it this way, we must take two integrals. It may be too much work. An easier way is we can think of negative angle. If we rotate this way down, if we go down from 0, this angle 11 pi over 6 is the same as negative pi over 6. If we rotate clockwise in this direction, 11 pi over 6 is equivalent to negative pi over 6. Then we start from negative pi over 6, go all the way to 7 pi over 6. From negative pi over 6 to 7 pi over 6. We get exactly the same area. From negative pi over 6 to 7 pi over 6. If we solve it this way, we only need one integrals. Half of r squared d theta. This way is easier than solving two integrals. So let me solve it this way. From negative pi over 6 to 7 pi over 6. Half of r squared. R is 1 plus 2 sine theta square d theta. First of all, we need to take antiderivative. For half of 1 plus 2 sine theta squared, the antiderivative, we solved it already. It's 3 over 2 theta minus 2 cosine theta minus half of sine 2 theta. So take the antiderivative, it's the same as the previous part. The antiderivative is 3 over 2 theta minus 2 cosine theta minus half of sine 2 theta. Evaluate from negative pi over 6 to 7 pi over 6. Then plug in 7 pi over 6 and negative pi over 6 and take the difference. If we plug in 7 pi over 6, in the previous problem, we know it already. In the previous part, we know it already. It's 3 over 2 times 7 pi over 6 minus 2 times negative radical 3 over 2 minus half times radical 3 over 2. If we plug in negative pi over 6, we have 3 over 2 times negative pi over 6. Cosine negative pi over 6 is positive radical 3 over 2. If I plug in negative pi over 6 here, 2 times negative pi over 6 is negative pi over 3. Sine negative pi over 3 is negative radical 3 over 2. Then try to combine like terms here. Combine these two terms. 7 pi over 6 minus negative pi over 6 is 8 pi over 6. 8 pi over 6 is the same as 4 pi over 3. 4 pi over 3 times 3 over 2 is 2 pi. Cancel 2 here. Double negative is positive. I get radical 3. Cancel 2 here. Double negative is positive. I get another radical 3. Radical 3 plus radical 3 is 2 radical 3. Last term I get radical 3, negative radical 3 over 4. Last term here, triple negative is negative. I get negative radical 3 over 4. Combine like term, that's radical 3 over 2. Negative radical 3 over 2. Then combine like term here, I get 2 pi plus 3 radical 3 over 2. That's an area enclosed by the outer loop. Number 4, part B. Let R1 equal to 2 cosine 3 theta and R2 equal to 1. Find the area of the region inside the first curve and outside the second curve, and the area of the region inside both curves. First of all, let's sketch a graph for both curves. R1 is 2 cosine 3 theta. The graph looks like this. That's R1. R2 equal to 1. That's a circle of radius 1. That's a circle of radius 1. We are first of all looking for the area inside the first curve but outside the second curve, which means this part. Area inside the first curve but outside the second curve. That's what we are looking for. So these three pieces, they are symmetrical, they are exactly the same. And for the first piece, first piece here, I can find half of this region. I can find half of this region here. Then multiply by 6. That's the total area. Inside the first curve, outside the second curve. Find the area here. Multiply by 6. That's the total area. Inside the first curve, outside the second curve. So let me zoom in. Make this region a little larger. If I zoom in, I get this. That's what we are looking for. So I can try to find the area between these two curves. I can try to find area between these two curves. At this line here, we know theta is 0. And what's theta here? For theta at this point, I set R1 equal to R2. I can solve for theta. I can set R1 equal to R2 and solve for theta in the first quadrant. So I set R1 equal to R2, solve for theta. That's the upper bound of the curve. So set R1 equal to R2. I have 2 cosine 3 theta equal to 1. Cosine 3 theta equal to a half. We know for cosine function in the first quadrant, cosine pi over 6 is a cosine pi over 3 is a half. In the first quadrant, cosine pi over 3 is a half. So 3 theta must be pi over 3. If I solve for theta, theta must be pi over 9. So at this point, at the intersection here, theta is pi over 9. So I find the area enclosed by the further curve minus the area enclosed by the closer curve. So for the area here, I take 6 multiplied by this area. So this area enclosed by the further curve. Further curve is R1. Minus the area enclosed by the closer curve. Closer curve is R2. Then we substitute R1 and R2. R1 is 2 cosine of 3 theta. R2 is 1. Expand the perfect square. 2 square is 4. 4 times half is 2. The second integral, half times 1 square is half. Then apply half angle identity. Cosine square 3 theta can be rewritten as half of 1 plus cosine 6 theta. Two times half is 1, they get cancelled. And since for both integrals, since the limits are exactly the same, you can combine these two integrals together. 1 minus half is half. Then take antiderivative. I get half theta plus 1 over 6 sine 6 theta, evaluate from 0 to pi over 9. If I plug in pi over 9, I have half times pi over 9 plus 1 over 6 times, if I plug in pi over 9 here, 6 times pi over 9 is 2 pi over 3. Sine 2 pi over 3 is radical 3 over 2. If I plug in 0, I get 0. So half times pi over 9 is pi over 18. Radical 1 over 6 times radical 3 over 2 is radical 3 over 12. Then distribute 6. I get pi over 3 plus radical 3 over 2. Next, find the area of the region inside both curves. Let me draw the curve again. That's R1. 2 cosine 3 theta. R2 equal to 1. It's a circle. Find the area of a region inside both curves. That's a region inside both curves. We can see that these three pieces, they are exactly the same. Again, we can find half of the first piece, then multiply by 6. And we get the total area inside both curves. We can find half of the first piece, then multiply by 6. We get the total area inside both curves. So let me zoom in. For this region, let me zoom in. If I zoom in, it looks like this. If I zoom in, this region looks like this. I can cut into 2 pieces. First piece is bounded by R2. A1 is bounded by R2. A2 here, second piece, A2 is bounded by R1. Here, first region is bounded by R2. Second region is bounded by R1. Adding up, we get an area from the first piece here. Then multiply by 6, we get the total area inside both curves. So for A1, A1 is from 0 to the intersection. From the previous part, we know the intersection is pi over 9. So A1 is bounded by theta from 0 to pi over 9. A1 is from 0 to the intersection. From the previous part, we know the intersection here is theta is pi over 9. Theta is pi over 9. And this region, A1 is bounded by R2. For A2, A2 is bounded by R1. And it's from pi over 9. Start from this point, go back to the origin. R1 start from this point, go back to the origin. So it starts from pi over 9 to some value here. How do we find this value? We know when R1 go back to origin, we set R1 equal to 0. I can solve for theta. When R1 go back to origin, we can set R1 equal to 0. Then solve for theta. The theta is the upper limit. So I set R1 equal to 0. Set R1 equal to 0. I get 2 cosine 3 theta equal to 0. Cosine 3 theta equal to 0. cosine of pi over 2 is 0. Cosine of pi over 2 is 0. So 3 theta equal to pi over 2. Divide both sides by 3, theta equal to pi over 6. So when theta is pi over 6, R1 go back to 0, go back to the origin. So the upper bound is pi over 6. Upper bound is pi over 6. Then evaluate both integral, I can find R1, R2. Then find the sum, multiply by 6. I get the total area. Let me compute each A1 and A2 individually. R2 is 1. Half times 1 is half. Take antiderivative. We get half of theta, evaluate from 0 to pi over 9. If I plug in pi over 9, I get pi over 18. If I plug in 0, I get 0. That's A1. That's A1 here. Next, let's compute A2. Take integral from pi over 9 to pi over 6. Half of R1 squared. R1 is 2 cosine 3 theta squared d theta. Simplify, I get 2 cosine squared 3 theta. Then apply half angle identity. I get 2 times half of 1 plus cosine 6 theta d theta. 2 and a half get cancelled. Take antiderivative. I get theta plus 1 over 6 sine 6 theta. Evaluate from pi over 9 to pi over 6. If we plug in pi over 6, I get pi over 6 plus 1 over 6 times, if I plug in pi over 6 here, 6 times pi over 6 is pi, sine pi is 0. If I plug in pi over 9, I get pi over 9 plus 1 over 6 times, 6 times pi over 9 is 2 pi over 3. Sine 2 pi over 3 is radical 3 over 2. So combine like terms, pi over 6 minus pi over 9, that's pi over 18, minus radical 3 over 12. So that's A2, that's area of this small region here. Then from the total area inside both curves, I take A1 plus A2 times 6. A1 plus A2 times 6, which is pi over 18 plus pi over 18 minus radical 3 over 12. That's pi over 3, distribute 6, I get pi over 3 plus pi over 3 minus radical 3 over 2. Combine like terms, I get 2 pi over 3 minus radical 3 over 2. Number 4, part C. Let R equal to 4 sine theta. Find the length of an arc for one loop. We know that the arc length formula for polar function is square root of r squared plus dr over d theta squared d theta, theta from alpha to beta. This formula is simple. The hardest part is finding the upper and lower limit. So let's sketch the graph first. For r equal to 4 sine theta, its graph looks like this. We know that when theta is 0, we are here in the origin. we try to find out for which theta value it complete one cycle. It complete the first cycle. For which theta value it complete the first cycle. So when the curve complete the first cycle, it goes back to origin. It goes back to origin. So I set r equal to 0. I set r equal to 0. If I set r equal to 0, I have 4 sine theta equal to 0. Divide both sides by 4. Sine theta equal to 0. If we solve the equation for theta, theta must be 0, plus minus pi, plus minus 2 pi, plus minus 3 pi, and so on. So if we rotate counterclockwise, the first theta value that go back to origin is pi. So when theta equal to pi, this curve go back to origin. So the limit is from 0 to pi. Square root of r squared. R is 4 sine theta plus dr over d theta squared. If I take derivative for r, I have 4 cosine theta. So plug in. I get 4 cosine theta squared d theta. Then simplify what's under square root. I have square root of 16 sine squared theta plus 16 cosine squared theta d theta. If we combine like terms, we get 16 times sine squared theta plus cosine squared theta. And we know that sine squared theta plus cosine squared theta is 1. So what's under square root is 16. Square root of 16 is 4. Take antiderivative with respect to theta. I get 4 theta. Evaluate from 0 to pi. If I plug in pi, I get 4 pi. If I plug in 0, I get 0. So the answer is 4 pi. Number 5. For each of the following pairs of vectors, find the angle between the vectors and find a unit vector which is orthogonal to both vectors. Part A. The vectors are 1, 1, 1 and 2, 1, negative 1. For an angle between two vectors, we can use the formula. Cosine theta between two vectors is dot product v1 dot v2 over the magnitude of v1 times magnitude of v2. So for the numerator, we do dot product v1 dot v2. 1 times 2 is 2. 1 times 1 is 1. 1 times negative 1 is negative 1. On the denominator, magnitude of v1 is square root of 1 square plus 1 square plus 1 square. Magnitude of v2 is 2 square plus 1 square plus negative 1 square. Then multiply out. Numerator 2 plus 1 minus 1 is 2. Denominator 1 plus 1 plus 1 is 3. Another square root. 2 square is 4. 4 plus 1 plus 1 is 6. Radical 3 times radical 6 is radical 18. If I simplify, radical 18 can be rewritten as 3 radical 2. That's radical 2 over 3. Then I can solve for theta. Theta is inverse cosine of radical 2 over 3. Using calculator, it's about 61.87 degrees. Then for the unit vector, which is orthogonal to both vectors, we first of all compute the cross product. Cross product generates a vector that's perpendicular to both vectors. So compute the cross product, that v equal to v1 cross v2. put ijk in the first row, put a standard base ijk in the first row, write v1 in the second row, and write v2 in the third row, 2, 1, negative 1. Then compute the determinant. Compute the determinant. I times 1, 1, 1, negative 1 minus j times 1, 1, 2, negative 1 plus k times 1, 1, 2, 1. Next, compute the determinant. First component is negative 1 minus 1. Second component is negative 1 minus 2. The third component is 1 minus 2. If I write it as a vector, I have negative 2, 2, double negative is positive, that's 3. 1 minus 2 is negative 1. That's a vector. That's a vector which is orthogonal to both v1 and v2. Then, in order to find a unit vector, I take vector v divided by its magnitude. Which is negative 2 square plus 3 square plus negative 1 square. Negative 2 square is 4, 3 square is 9, negative 1 square is 1. 4 plus 9 plus 1 is 14. So the unit vector is negative 2 over radical 14, 3 over radical 14, and 1 over radical 14. This is a unit vector which is orthogonal to both vectors. Number 5, part B, the same procedure. Find the angle between two vectors and find a unit vector which is orthogonal to both vectors. Let's find the angle first. Cosine theta is the dot product v1 dot v2 over magnitude of v1 times magnitude of v2. Let's do the dot product first. v1 dot v2. 3 times 2 is 6. 2 times negative 3 is negative 6. 1 times 0 is 0. On the denominator, compute the magnitude for v1 and v2. I have 3 square plus 2 square plus 1 times square root of 2 square plus negative 3 square plus 0 square. In the numerator, 6 minus 0 plus 6 minus 6 plus 0 is 0. Denominator, I have 3 square is 9, 2 square is 4, 1 square is 1, that's radical 14, times another square root of 2 square is 4, negative 3 square is 9, 0 square is 0, 4 plus 9 is 13. 0 over radical 14 times radical 13 is 0. So cosine of theta is 0. That means theta is inverse cosine of 0. Inverse cosine of 0 is 90 degrees. Next, we try to find unit vector which is orthogonal to both vectors. So let's find a vector first. Let's find a vector that is orthogonal to both vectors first. The v equal to the cross product v1 cross v2. v1 cross v2 generates a vector that is perpendicular to both v1 and v2. Put ijk in the first row. Put v1 in the second row. Put v2 in the third row. Then take determinant. I times 2, 1, negative 3, 0, minus j times the matrix 3, 1, 2, 0, plus k times the matrix 3, 2, 2, negative 3. Then compute the determinant. 0 plus 3. 0 minus 2. Negative 9 minus 4. If I write it as a vector, I have 3, 2, negative 13. That's a vector which is orthogonal to both v1 and v2. In order to find a unit vector, I take vector v divided by its magnitude. Take vector v divided by its magnitude. That's a unit vector pointing in the same direction. So I have 3, 2, negative 13 divided by its magnitude. That's 3 square plus 2 square plus negative 13 square. 3, 2, negative 13 divided by square root of 3 square is 9, 2 square is 4. Negative 13 square is 169. 9 plus 4 is 13. 13 plus 169 is 182. So the answer is 3 over radical 182, comma 2 over radical 182, comma negative 13 over radical 182. That's a unit vector which is orthogonal to both v1 and v2. Number 6, part A. Find the equation of the line perpendicular to the plane 2x minus 3y plus 6z equal to 5 and passing through a point 3, negative 1, negative 4. Let me draw the picture first. Assume that's the plane. Assume that's the plane 2x minus 3y plus 6z equal to 5. We are looking for equation of a line perpendicular to the plane. Assume that's the line that perpendicular to the plane. Assume this line is perpendicular to the plane. We're looking for a line that perpendicular to the plane and passing through a point 3, negative 1, negative 4. If this line is perpendicular to the plane, then its directional vector is parallel to the normal vector of the line, of the plane. If this line is perpendicular to the plane, then its directional vector is parallel to the normal vector of the plane. So we can use the normal vector as the directional vector of the line. So I can take v equal to the normal vector. Since they are parallel, they point in the same direction. Since they are parallel, they point in the same direction. So I can take v equal to n, equal to the normal vector. Normal vector is 2, negative 3, and 6. In order to find equation of a line, we also need to know a point on the line. Here we have it here, 3, negative 1, negative 4. That's a point on the line. So R0 is 3, negative 1, negative 4. And the equation of a line is R of t equal to R0 plus t times v, where R0 is a point on the line and v is the directional vector of the line. R0 is 3, negative 1, negative 4. V is 2, negative 3, and 6. Distribute t and add the vectors. I have 3 plus 2t, negative 1 minus 3t, negative 4 plus 6t. If we write the line as a parametric equations, we have x equal to 3 plus 2t, y equal to negative 1 minus 3t, z equal to negative 4 plus 6t, where t can be any real number. That's an equation of the line, perpendicular to the plane and passing through the point 3, negative 1, negative 4. Number 6, part B. Find the equation of a plane perpendicular to a plane x plus 4y minus 2z equal to 1 and passing through points 2, -1, 2 and 4, 3, 0. So here we are looking for equation of a plane perpendicular to a plane x plus 4y minus 2z equal to 1. Let me draw this plane first. Assume this is the plane x plus 4y minus 2z equal to 1. We are looking for equation for another plane that perpendicular to this plane. Next, let me draw the perpendicular plane. Assume this is a plane that perpendicular to the plane x plus 4y minus 2z equal to 1. We are looking for equation of this plane. And this plane contains 2 points. 2, -1, 2 and 4, 3, 0. If I join these 2 points, I can find a vector that lies on the plane. If I join these 2 points, I can find a vector that lies on this plane. And also, since these 2 planes are perpendicular, the normal vector of the given plane also lies on this plane. The normal vector of this plane, of the given plane, also lies on the plane. Once I know 2 vectors on the plane, I can find a cross product. I use cross product for the normal vector of the plane, of this plane. So once I know 2 vectors that lie on the plane, I can take a cross product that generates a vector that's perpendicular to this plane, which is the normal vector of the plane we are looking for. So join 2 points, I can find the first vector that lies on the plane. So V1, I join to these 2 points, I take head minus tail, 2, -1, head minus tail, 2 minus 4, comma, -1 minus 3, comma, 2 minus 0. So the first vector here is -2, -4, and 2. For the second vector lies on the plane, I can take the normal vector of the given plane. The normal vector of the given plane is 1, 4, -2. So those are 2 vectors that lie on the plane. Next, by taking the cross product, I can find a vector that's perpendicular to both vectors here, which is the vector that's perpendicular to the entire plane. So take normal vector, take cross product, I can find a normal vector, which is I, J, K. Put IJK in the first row, put V1 in the second row, and put V2 in the third row. Then take determinant, I times the determinant of the matrix -4, 2, 4, -2 minus vector j times the determinant of the matrix -2, 2, 1, -2 plus vector k times the matrix times the determinant of the matrix -2, -4, 1, and 4. Then compute determinant. That's A minus A. 4 minus 2. That's negative a plus 4. Then write this in vector form. I have 0, comma, negative 2, comma, negative 4. And here for normal vector, I can make it a little simpler. This is v1 cross v2. If I factor, I can pull out negative 2. And pull out negative 2, I have 0, 1, 2. I can take this to be my normal vector, which is simpler than this expression. So I take my normal vector to be 0, 1, and 2. So this is normal vector, and we know a point on the plane. Equation of a plane is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0, where a, b, c is the component of the normal vector. x0, y0, z0 is a point that lies on the plane. So the component of the normal vector is 0, 1, and 2. A point that on the plane. Here, make it a little easier. I can use 4, 3, 0. S minus 4, y minus 3, z minus 0. Then simplify. First term becomes 0. Second term is y minus 3. Then distribute 2, I get 2z. For the final answer, put the variables on one side. Move constant to the other side. So y plus 2z equal to 3. That's the plane. That's perpendicular to the given plane and contains these 2 points. Number 6, part C. Find the equation of a plane containing a line s equal to 2 plus t, y equal to 3t, z equal to 3 minus 2t, and passing through a point negative 2, comma, negative 3, comma 1. So we are looking for equation of a plane that contains a line and a point. This point is negative 2, negative 3, and 1. We're looking for equation of this plane that contains this line and this point. So we know that the directional vector, since this line lies on the plane, the directional vector of the line lies on the plane. Since this line lies on the plane, its directional vector lies on the plane. And also, if I join a point on the line and a given point here, I can find another vector that lies on the plane. If I join a point on the plane and this given point, I can find a vector that's also lies on the plane. Once I have 2 vectors on the plane, by taking the cross product, I can find a normal vector of the plane. Once I know 2 vectors, by taking the cross product, I can find a normal vector of the plane. So this line on the plane is 2x equal to 2 plus t, y equal to 3t, z equal to 3 minus 2t. Its directional vector v is 1, 3, negative 2. That's the directional vector of the line, which lies on the plane. Let's call this vector v1. Now, next, I can pick point on the line. If I let t equal to 0, a point on the line is, if I let t equal to 0, a point on the line is 2, 0, 3. There's a point on the line. Then I can join this point and a given point. I can find another vector that lies on the plane. So join these 2 points. I can use head minus tail. For v2, I can use head minus tail. Negative 2 minus 2. Negative 3 minus 0. And 1 minus 3. This vector is negative 4, comma, negative 3, comma, negative 2. So here we have two vectors that lie on the plane. By taking cross product, I can find the normal vector. So v1 cross v2, I can use cross product here. Write I, j, k in the first row. Put v1 in the second row. 1, 3, negative 2. Put v2 in the third row. Negative 4, negative 3, negative 2. Then take cross product. I have I times determinant of the matrix 3, negative 2, negative 3, negative 2, minus j times determinant of the matrix 1, negative 2, negative 4, negative 2, plus k times the matrix times the determinant of the matrix 1, 3, negative 4, negative 3. Then take determinant. I times negative 6 minus 6 minus j times negative 2 minus a plus k times negative 3 plus 12. Write this in vector form. I have negative 12, positive 10, and positive 9. In general, for normal vector, we try to make the first component positive. So I can pull out negative 1. I have 12, negative 10, negative 9. So take this as my normal vector. 12, comma, negative 10, comma, negative 9. Then equation of a plane is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equal to 0, where a, b, c is the component of the normal vector, and x0, y0, z0 is a point that lies on the plane. So here ABC is 12, negative 10, and negative 9. A point on the plane, I can use negative 2, negative 3, and 1. X plus 2, y plus 3, z minus 1. Then distribute, combine like terms. If I distribute 12, I get 12x plus 24. If I distribute negative 10, I get negative 10y minus 30. If I distribute negative 9, I get negative 9z plus 9. Then add the constant together. 24 minus 30 is negative 6. Negative 6 plus 9 is positive 3. If I move positive 3 over, it becomes negative 3. And the variables here we have 12x minus 10y minus 9z. That's the equation of the plane that contains this line and this point. Number 7, part A. Verify that two planes 2x minus 4y plus 6z equals 3 and 3x minus 6y plus 9z equal to a are parallel, and find the distance between two planes. Let's first of all verify these two planes they are parallel. First plane is 2x minus 4y plus 6z equal to 3. Second plane is 3x minus 6y plus 9z equal to a. If two planes are parallel, their normal vector must be parallel. So let's verify their normal vector. Normal vector of the first plane is 2, negative 4, and 6. normal vector of the second plane is 3, -6, and 9. Are they parallel? Let's verify the ratio of each component. 2 divided by 3 is 2/3. For the first component, 2 divided by 3 is 2/3. For the second component, -4 divided by -6 is also 2/3. For the third component, 6 divided by 9 is also 2/3. If the ratio of each component is the same, that means n1 equal to 2/3 of n2. If the ratio is the same, it's 2/3 everywhere, that means n1 equal to 2/3 of n2. So they are parallel. If one vector is a multiple of another vector, they are parallel vectors. So since their normal vectors are parallel, these two planes are parallel. Next, we try to find the distance between these two parallel planes. Here we use the formula d equal to absolute value of vector pq dot vector n over the magnitude of vector n. In this formula, point P represents a point in the first plane, Q represents a point in the second plane, and vector n represents a vector that's perpendicular to both parallel planes. Let me find point P and Q first. In the first plane, if I let y equal to 0 and z equal to 0, then I have 2x equal to 3. So x component is 3/2. So a point in the plane could be, a point on the plane is 3/2, 0, 0. That's point P. So P is a point 3/2, 0, 0. In the second plane, do the same thing. Let y equal to 0 and z equal to 0. Then we have 3x equal to a. If I solve an equation for x equal to a/3, that's an s component. So a point on the second plane is a/3, 0, 0. That's point Q. So vector PQ, we can use head minus tail. a/3 minus 3/2, 0 minus 0, 0 minus 0. That's 7/6, 0, 0. So that's vector PQ. Next, we try to find vector N. N is a vector that's perpendicular to both planes, to both parallel planes. So in order to find N, we can use either N1 or N2. Since they are parallel vectors, we can use either N1 or N2. N1 is 2, -4, and 6. To make N a little easier, I can pull out 2. If I pull out 2, I have 1, -2, and 3. Take this vector to be vector N. Take this vector to be vector N. Next, once I know vector PQ and vector N, I can find the distance. I can use the distance formula to find the distance between these two parallel planes. So the distance is PQ dot N over magnitude of vector N. If I take dot product, take absolute value of the dot product, 7/6 times 1 is 7 over 6. 0 times negative 2 is 0. 0 times 3 is 0. That's the absolute value of the dot product. Denominator is the magnitude of vector n. It's square root of 1 square plus negative 2 square plus 3 square. So if we simplify the top and the bottom, I have 7 over 6 over square root of 1 square is 1, negative 2 square is 4, 3 square is 9, 1 plus 4 plus 9 is 14. This can be rewrite as 7 over 6 radical 14. If we try to rationalize the denominator, I can multiply top and the bottom by radical 14. So this term can be rewrite as 7 times radical 14 over 6 times 14. If I cancel 7 from top and bottom, I have radical 14 over 12. That's the distance between these two parallel planes. Number 7, part B. Verify that two lines L1 and L2 are skewed and find the distance between two lines. If we try to verify two lines are skewed, we need to show that they are not parallel and they are not intersecting. Let's first of all verify that L1 and L2 they are not parallel. So the directional vector in the first line is negative 3, 4, and 2. Negative 3, 4, and 2. The coefficient of t is the directional vector of the first line. Negative 3, 4, and 2. The directional vector of the second line is negative 2, positive 2, and positive 3. We can see that this component has different ratios. Each component has different ratios, so they are not parallel. Since V1 is not parallel to V2, then we know that L1 and L2 they are not parallel. Next, we try to verify that they are not intersecting. These two lines they are not intersecting. When two lines intersect, the S component must be the same as the S component. The Y component must be the same as the Y component, and the G component must be the same as the G component. So we set S component equal to S component, Y component equal to Y component, G component equal to the G component for both lines. 1 minus 3t equal to 3 minus 2t. 2 plus 4t equal to 2 plus 2t. Negative 1 plus 2t equal to negative 1 plus 3t. But this t value for these two lines, their t value may be different. So in the first line, let's call it their t value t1. For the second line, let's call their t value t2. Next, we try to solve these equations for t1 and t2. If this system of equation has a unique solution for t1 and t2, then two lines are intersecting. If this system of equation has infinitely many solutions, then two lines are identical. If this system is inconsistent, if this system of equations is inconsistent, then two lines skew. Let me rewrite each equation first. First equation can be rewrite as negative 3t1 plus 2t2 equal to 2. Second equation can be rewrite as 4t1 minus 2t2 equal to 0. Third equation can be rewrite as 2t1 minus 3t2 equal to 0. If I add the first two equations together, I have t1 equal to 2. If I substitute t1 into the second equation, I have a minus 2t2 equal to 0, negative 2t2 equal to negative a, t2 equal to 4. If I substitute t1 into the third equation, I have 4 minus 3t2 equal to 0, negative 3t2 equal to negative 4, t2 equal to 4 over 3. We have different solution for t2. So that means this system of equation is inconsistent. If the system of equation is inconsistent, that means two lines skew. So two lines are skew. That means they are not parallel and they are not intersecting. Next, let's try to find the distance between these two skew lines. Here we use the formula d equal to the absolute value of vector pq dot n over the magnitude of vector n. In this formula, p represents a point on the first line, q represents a point on the second line, and vector n represents a vector that's perpendicular to both line 1 and line 2. N is a vector that's perpendicular to both line 1 and line 2. So here let me find point P, Q, and vector n first. In line 1, let t equal to 0. Then P is the point. If I let t equal to 0, P is the point 1, 2, negative 1. In line 2, if I let t equal to 0, then Q is the point 3, 2, negative 1. So vector PQ, we use head minus tail, Q minus P. I get 2, 0, 0. That's vector PQ. Next, let's try to find vector n. N is a vector that's perpendicular to both line 1 and line 2. If n is perpendicular to both line 1 and line 2, it must be perpendicular to both directional vectors. So, directional vector of the first line. Directional vector of the first line is negative 3, 4, and 2. Directional vector of the second line is negative 2, 2, and negative 1. Sorry, negative 2, 2, and 3. So for vector n, I can take a cross product. N is a vector that's perpendicular to both v1 and v2. I can take a cross product. v1 cross v2 is, I put I, J, K in the first row. That's the standard base of R3. Then put v1 in the second row, negative 3, 4, 2. Put v2 in the third row, negative 2, 2, 3. Then take determinant for this matrix. I times the matrix, determinant of the matrix 2, 4, 2, 2, 3 minus J times the determinant of the matrix negative 3, 2, negative 2, 3 plus K times determinant of the matrix negative 3, 4, negative 2, 2. Then take determinant for this 2 by 2 matrix. 12 minus 4, negative 9 plus 4. Negative 6 plus a. Then when it's in vector form, I have a 5 and 2. That's the normal vector. Sorry, that's the vector that's perpendicular. That's a vector that's perpendicular to both line 1 and line 2. That's a vector that's perpendicular to both line 1 and line 2. That's a vector n. Then use the distance formula. Distance is the dot product of PQ and n. So 2 times a is 16. 0 times 5 is 0. 0 times 2 is 0. Over the magnitude of vector n. That's a squared plus 5 squared plus 2 squared. On the numerator, 16 plus 0 is 16. On the denominator, a squared is 64. 5 squared is 25. 2 squared is 4. 64 plus 25 is 89. 89 plus 4 is 93. So denominator is square root of 93. That's the distance between two skew lines. That's the distance between these two skew lines. Number 7, part C. Find the distance between a line s equal to 3 plus 2t, y equal to 1 plus t, g equal to -1 plus 2t, and a point 0, 2, 3. For distance between a line and a point, we here use the formula d equal to the magnitude of vector PQ cross vector V over the magnitude of vector V, where P is a point on the line, Q is a point outside the line, Q is the point outside the line, V is the directional vector of this line. So let's find vector PQ and vector N and vector V. So on the line, let t equal to 0. If I let t equal to 0, then point P is 3, 1, -1. And point Q is a point outside the line. Point Q is the point outside the line, not on the line. That's 0, 2, 3. So for vector PQ, we use head minus tail. 0 minus 3, 2 minus 1, 3 minus -1, which is -3, 1, and 4. That's vector PQ. Vector V. V is the directional vector of the line. V is the directional vector of the line, which is 2, 1, 2. Next, take cross product. Next, we take cross product. PQ cross V. Vector PQ cross V. Take cross product. Put vector I, J, K on the first row. Put vector PQ on the second row. Put vector V on the third row. That can be rewrite as I times, take determinant, I times determinant of the matrix 1, 4, 1, 2 minus J times determinant of the matrix -3, 4, 2, 2 plus vector K times determinant of the matrix -3, 1, 2, 1. Then take the determinant for this 2 by 2 matrix. 2 minus 4 J times -6 minus A plus K times -3 minus 2. Then write this as a vector. Write this in vector form. I have -2, positive 14, -5. That's the cross product. Then plug into the formula. Plug into the distance formula. This term formula is the magnitude of this cross product over magnitude of the directional vector v. So I have square root of negative 2 squared plus 14 squared plus negative 5 squared over square root of 2 squared plus 1 squared plus 2 squared. So numerator is negative 2 squared is 4. 14 squared is 196. Negative 5 squared is 25. 4 plus 196 is 200. 200 plus 25 is 225. The denominator, 2 squared is 4. 1 squared is 1. 2 squared is 4. 4 plus 1 plus 4 is 9. Square root of 225 over square root of 9 is square root of 25. Square root of 25 is 5. So the distance between the line and the point is 5.